Hello and welcome everyone. My name is Enrique Levine, co-founder and VP of Product at Zintro. Zintro is a global platform that makes it easy for companies to start a conversation with highly specialized experts, consultants, contractors, and job candidates about potential phone consults, projects, or employment opportunities. Specialization spans all industry sectors, technical disciplines, job functions, and geographies. Today's webinar, How to Automate Software Development and Engineering, will be presented by Stephen F. Hafner, President of XTRAN LLC. It is with great pleasure I introduce Zintro expert Stephen F. Hafner. Stephen has been an enterprise systems architect since 1964, an international consultant since 1972, a software entrepreneur since 1977, a Wharton professor from 1983 to 1994, and also an expert witness. He is the creator of XTRAN, an expert system Metatool for automating the assessment, transformation, and translation of computer languages, data, and text. If you would like to ask Steve any specific questions, feel free to use the questions section of your GoToWebinar control panel, or the little orange arrow on the top right corner of your screen. Just click on that, and on the question section, write your question at any time throughout the webinar. Steve will respond to questions after the presentation. So stay tuned. We will be providing Steve's contact information also at the end of this webinar for follow-ups. Without further ado, I'd like to turn it over to our presenter, Stephen F. Hafner.
Thanks, Enrique. Welcome, everyone. What we're going to talk about today is the automation of the software development and engineering process. Now, software delivery has been getting quite a bit of automation attention lately. We've got build configuration, make, the old make, and things like that, which control an actual building process. Source code control, of course, with the old RCS and SACS from Unix, CVS, Git is one of the more active ones these days. And then we've also got some automatic code generation from models, what's called model-driven architecture or model-driven development. And then we've also got testing automation with things like JTest and other frameworks for doing testing. But none of those alternatives actually addresses existing code. So what do we have in the way of alternatives for existing code? Well, basically, I see two. One is what we call point solution tools for analyzing, transforming, or translating code. And the other one, which is what I'm going to be talking about today, is a rule-driven expert system, which can automate basically all activities that involve existing code. It's a different way to look at the software development and engineering process. We like to break down software engineering activities that involve existing code into several broad categories. The first is code analysis, in which we pull information out of the code, but we don't change the code. The second is what we call code reengineering. That means that we apply transformations to the code. We don't change its language, but we change its quality or what it does. The third broad category is translation. This means transforming the functionality of the code to a different language, usually to the same or a higher level, and I'll talk about that a little bit more. And then the special case of translation is code generation, where we're going from higher level to lower level, sometimes referred to as compilation. Okay, let's break those down a little bit further. In terms of analysis, there are three categories within that we like to identify as well. One of them is what we call code demographics. This is information about the code. You can think of it as basically pulling the architecture out of the code itself, because as somebody once said, the only absolutely guaranteed accurate representation of the architecture of code is the code itself. But it's not very useful in the code, so we've got to get it out. So that includes things like a module function cross-reference. For each module, what functions does it declare, what functions does it call, and then in the other direction, for each function, what module declares it and which modules call it. Similarly, we have the function calling tree, which is functions calling functions. We have, in languages that allow inclusion of code, for example, C and C++ have the include statement, COBOL has the copy statement with copybooks. That creates a dependency tree as well, where we've got main programs or modules copying or including things. Those included files can also do includes and so forth. And again, we want that both directions. And then we're interested in global symbols because they represent, in a sense, the state of an application system. And again, we want that cross-referenced in both directions. And then there are measurements, things like statements per function. Okay, so that's what we call demographics. That's kind of the lay of the land. Then there's code quality measures. And code quality is fortunately getting a lot of attention these days, as I think it should. And there are lots and lots of code quality measures. Cyclomatic complexity, which Tom McCabe came up with, is a measure of it's a count of the number of logic paths through a function. Halstead's volume is a rather complex calculation that gives you a measure of how heterogeneous code is, how homogeneous it is in terms of things like style and the use of language features. Go-tos, everybody hates go-tos. Actually, in their place, they can be a good thing, but they're usually abused. So we're interested in them. Knots, which are go-to crossings, are interesting because they defeat readability and they also make it difficult to structure the code to get rid of go-tos. Then we've got dead code, which is code that nobody ever calls. And we've got cloned code, which is cut and pasted, which is a bad practice because, of course, it creates parallel maintenance paths. So if you find a bug, then you've got to go find all the places that code was cut and pasted to and fix the bug there as well. And then we've also got coding standards and conventions. If I'm a software development manager, I'm going to establish standards and conventions for my developers to follow so that we've all got the same styles, conventions for how we abbreviate things, and so forth and so on. For example, I might say you can't have more than 3 levels of if, nested ifs, because that gets too hard to read. Okay, and one of the things about coding standards and quality is that measuring it is critical. That's the only way you can really control it, so we need to automate that. And then the third category of analysis is what we think of as ad hoc. In other words, these are things that crop up from time to time. Let's say that I'm a development manager and I'm looking at our in-house function library or class methods, and I decide that adding a parameter to a function is going to make it a lot more useful to a lot more people. So I go to my developers and I say, I want to add a parameter to this function. What is the impact of that? Where is this thing called? What are we going to have to do to implement this change, this upgrade? And frequency of occurrence is critical, as is location of those calls throughout a system. So we need to figure that out as well. Now let's move on to reengineering. Basically here we're talking about changing the code by applying transformations to it. And kind of paralleling our analysis breakdown, we've got code quality improvement. For example, we would like to get rid of those go-tos that we decided were evil. So we want to structure the code, impose if, else, do, while, and for in order to eliminate go-tos. Similarly, if we've got cloned code, we want to get rid of that by refactoring and eliminating the duplication. That's going to help us with maintenance a lot. If we've got dead code, there's no point in having it around, although I recommend a post-mortem on the corpse to make sure it really is dead and see whether we might someday want to bring it back to life before we get rid of it. Some programmers write their code at too low a level because they're novices, for example. And it might be possible to raise the level of the code to, we call it decompilation, to get it to a higher level where it's easier to understand and maintain. And then, of course, there's coding standards and conventions, which I talked about under analysis. Let's say that I'm company A and I acquire company B, and in the door with company B comes a whole bunch of code. Now, of course, that code is not coded to the standards and conventions that we have in company A, and we're going to have to retrofit our standards and conventions onto that code that we just acquired. So that's something that needs to be done as well. And then let's say that we're going to move our application system to a new platform. Well, there's several things involved there. First of all, there are going to be different functions to call. There are going to be different data structures. And there may even be different preprocessor constructs if we're dealing with languages that have them, such as assemblers, C and C++, PL1, and so forth. So there's going to be a whole bunch of transformations that are going to need to be done. Fortunately, they're very systematic. We have a set of functionality in the way it was done on our old platform. We've got similar functionality on the new platform done somewhat differently, but the transformations pretty much are can be bounded to a fixed set. And then lastly, going along with our ad hoc analyses that we need to do from time to time, things crop up. For example, if I do decide, based on my analysis, that I want to add a parameter to one of our functions, then we need to automate that. That's a systematic transformation that we can apply across the code. In terms of translation, that's pretty obvious. You're moving code from one language to another. Why would you want to do that? Well, languages fade and die, and they run out of gas. And when they do that, a number of bad things start to happen. First of all, the compilers and run libraries get less and less support, or alternatively, they get more and more expensive, or both. Secondly, because it's an old language and not too many people are using it anymore, development tool vendors don't tend to pay too much attention to it. So the development tools tend to languish and get stale and old. A lot of times a modern language will succeed because it provides more productivity for the developer, and we want to take advantage of that. And of course, with old languages, new programmers coming into the marketplace aren't too interested in them, so we get fewer and fewer as the old dinosaur programmers retire and take all that knowledge out the door with them, and so it gets harder and harder to find people who even know how to deal with the old language. And then we may have been in that old language for a reason that doesn't apply anymore. For example, let's say that 25 years ago, we implemented a whole bunch of stuff in assembler because we needed the speed. Well, nowadays with Moore's Law, our computers are much, much faster than they were then, so we can give up some of that relative speed and overcome that with a much faster modern computer. And of course, if we were in assembler, we were locked into that old platform. And that brings us to the next one, which is proprietary to portable languages. Let's say that I'm in a vendor's proprietary language, and it could be a computer manufacturer, it could be a 4GL vendor, whatever, but it's proprietary to them, it's not standardized, and that locks me into that vendor. If the vendor dies, obviously I have to get out and I might as well go to a portable language while I'm at it. But even if that's not the case, I may want to escape from that vendor lock-in in order to take advantage of stuff that's coming down the pike that vendor is not doing. Another scenario where we need to translate is I'm company A, and as I just mentioned, I bought company B, and in the door came all that code that we just talked about. But not only does it not conform to our standards and conventions, it's in different languages too. We're a PL1 shop, they're a COBOL shop, or we're a C++ shop, and they're a Pascal shop. So we need to rationalize all that and get our application portfolios rationalized to work better together to take full advantage of the synergies that are presumably one of the reasons that we as Company A bought Company B. And then we may also have historical legacies. We may have some code lying around that was written in a language years ago because that seemed like a good idea at the time, but now we would really like to have it in the language that everybody else is using. Okay, now I'm going to take a step back a little bit here and talk a little bit more philosophically for a second. We're going to be talking about meta a lot, and we need to figure out what we mean by meta. In a nutshell, to me, meta is information about information. In other words, it's one level of abstraction up from what I would characterize as the real world. Now, as a concept, it's been around for a long time. For example, metaphysicians have been talking about meta for hundreds of years. More recently, we've seen it start to be applied in enterprise architecture and IT. For example, in XML, I can not only transmit data as XML, but I can also talk about the data in terms of metadata in that same XML. So I carry not only the data, but information about it as well. That's metadata. Similarly, we can have models that are actually meta models, which can spawn a bunch of different kinds of models by binding them to a particular situation. I'll give an example of that. The Zachman framework, which you might be familiar with, is, in my view, a meta model for enterprise architecture, and I've suggested that to John Zachman, and he agrees with me. It is, in fact, an ontology, but it's also a model that is meta, and that means that we can then instantiate an actual enterprise architecture by binding things that are abstracted in the meta model to create a model. Now, it's a different way to think about automating software engineering. As I mentioned, most of the automation that's taken place so far has been in the form of point solutions, which are dedicated to specific tasks. You can also have meta about meta, which is 2 levels up from the real world. In the work I do meta every day. I do meta frequently, and I even do triple meta from time to time, although that's fairly rare. Now, when you abstract up to get to the meta level that we're talking about here, the only way you can do that is if you have an ontology that allows you to see what's common across the stuff that you're abstracting up from. So we need a conceptual ontology, then we need a semantic ontology, so we're all talking the same language, and that allows us to do that abstracting. So we're going to talk about that a little bit too. From my point of view, I think that the future of IT and even more broadly enterprise architecture lies with meta. I think it's a way to look at the world that is more powerful, and that has some implications we'll talk about in a little bit. Okay, in fact, what are the implications of meta for IT and for enterprise architecture? First of all, when you abstract up from detail, it allows you to integrate horizontally across problem domains. You can think about this as, one way to think about it is breaking down silos to see what they have in common and where they can work better together. You can also integrate vertically through using Metatools to capture that abstraction and manipulate that abstraction in a vertical situation. Another neat thing about abstraction is that it reduces complexity. Now, it doesn't really reduce it, it hides it. Basically what we're going to do is we're going to abstract up, we're going to use that abstraction and manipulate it to effectively relegate the complexity to a lower level where we can manipulate it more easily. And another thing about abstraction is that it reduces the rate that things change. The higher you go in an abstraction, the less frequently it's going to change. And we see that with the enterprise architecture in an enterprise. The architecture of an enterprise changes less rapidly than the details that populate that architecture, which is a good thing. Okay, one of the things that meta does is it gives you leverage. If you think about a situation, let's say we're a software development shop and we have no tools at all. We're just hard coding everything to the bare metal, more or less. Well, we put a lot of effort in and our results aren't that great because we don't have leverage. If we start to use some point solution tools from various vendors to automate certain aspects of what we're doing, then we begin to get better leverage, but we're really not in control of it very much because we're dependent on those vendors. We're dependent on what tools are available in the marketplace to provide that leverage as well. However, if we move to a meta tool and we use a rules language to create the tools we need when we need them, then we can regard leverage as a business decision. That is, we can invest in rules to push that leverage point as far left as is practical to do to get return on our investment in doing that and reduce the effort to get a larger result. So I've talked about point solutions a little bit. Let's just drill down on that a little bit better. When I talk about a point solution, I'm talking about a particular task that a vendor decides to automate. A vendor looks around the marketplace and says, here is a point where users are feeling pain. So I'm going to create a tool that addresses that pain point. And because it's a tool that's dedicated to that particular problem, there may be a little bit of flexibility in it, but basically it does what it does. And it can't really do other software development task automation. Not only that, but the vendor has decided what the input format should be, stuff going in, and what the output format should be, and what the script should be, and so forth. So all of that is typically very tool specific. On the other hand, a meta tool is an abstraction level up from that. It's not specialized for a particular point of pain. It is rule-driven, and with an appropriate rules language, and we'll talk more about that in a minute, it means that I can create tools fairly rapidly. And that's why, since it's a tool for creating tools, we call it a meta tool. Just like meta is information about information, this is a tool to create tools. Now, the best way to do that, in our view, is with an expert system whose domain of expertise is computer languages, data, and text. An expert system has a rules language. That's how you capture the expertise. In this case, we want one that is both general purpose and enriched for the job that it needs to do, which is automate software engineering. So you can think of it as a general purpose language that is very enriched with primitives that address typical software engineering automation tasks, which makes it also a domain-specific language. It's kind of a hybrid of the two. We want our rules language to be accessible to senior developers. We're not going to ask normal developers to learn it because it's probably a little too heavy duty for them. But senior developers should be able to learn it in a reasonable amount of time, not just crazy people in the back room being fed raw meat. We want it to be real world, and we want to deploy it throughout our enterprise to get maximum benefit from it. So what are we looking for? We're looking for a lot of leverage on the effort that we invest. And we're also looking for the ability to reuse expertise, even when the expert's not available, and on a scale that the expert can't do as an individual. Now, then another neat thing about this approach is that the software engineering automation that we do with this meta tool is under our control. We're the ones that are manipulating our code through the rules language, so we're in control of that. We don't have to go to a tool vendor, hat in hand, and say, your tool is nice, but it doesn't do X, and we need that X. So when can you give that to us? And the vendor comes back and says, well, I'm sorry, that doesn't really fit into my marketing plans. Or the vendor may say, yeah, that's a good idea, but we've got a lot on our plate right now, so you might see this in 6 months. So let's see what is involved in using a meta tool to create a solution that will automate something for us. If you look at this graphic, the pink area is a solution. It's a point solution, in fact, that we are creating with our meta tool. Let's see what's in there. First of all, we've got standard rules that came with the meta tool, and we're looking for a lot of standard stuff so we can start using it right out of the box, and we can reuse a lot of the work that the meta tool vendor has already invested. And then there's also the rules we develop, which of course we own. So that's the tool that we're creating. What comes into the tool? Well, basically code. It might also be data or text, depending on what we're doing. What comes out of the tool? If we're working with code, if we're analyzing, analysis results come out. And of course, we might want to put those into other tools, in which case we need to be able to get them out in a format that will go into other tools. It might be XML, it might be comma-separated values, so we can throw it into a database or a spreadsheet. Whatever we need, the meta tool should be able to create it in the form that we need. If we're re-engineering, then re-engineered code comes out, and that can go right back in for more re-engineering later if that's needed, so it becomes a cycle. And similarly, if we have translated it, then out comes our translated code in our new language, and that may actually have to go back in for more re-engineering later, or even maybe translation in the distant future when this language starts to fade. Okay. Another way to look at this is, in the upper tier there, we're using point solutions to do our automation. And we got a couple of problems. Number one is we need a bunch of them because each one can only do one or two things. And of course that also means that we've got multiple training. So we got to train our people on the first one, then the second one, and so forth. And they're quite different typically in terms of what you're being trained to do, so it tends to start getting kind of confusing. Contrast that with the Metatool. In the lower tier there, we see that the Metatool has a single training, which is in the rules language itself, and then depending on what rules you put into it, you can do lots of different things, lots of different tasks. And you can be a user, let's say a large software development shop in a large enterprise. You can be an ISV, an independent software vendor who's created a software product and is selling it, a payroll system or something. Or you can be an outsourcer, somebody who takes over maintenance and enhancement of code for somebody else and makes money that way. The point is that this Metatool is very generic in terms of what you can do with it, but at the same time it provides leverage, as we will see. Now I like to think in terms of tool chains. If I've got some language content, some code content, and I need to do a series of things to it to get it into shape. Let's say, for example, first I need to improve its quality. Then I need to move it to a different platform. And then I need to repurpose it to access it from the web, for example. Okay, that's a series of steps that need to be done to that code to get where I want to go. Well, if I'm trying to put together a tool chain from multiple point solutions from multiple vendors, I've got two problems. One of them is, as I mentioned, the input and output formats of these point solution tools tend to be vendor specific and tool specific. So the output from my first step may not match the input requirements of my second step, so I got a mismatch. Then the third step I need to do, there's no tool for. So I've got to fill that in somehow before I go on to the fourth step, for which there is a tool out there. So we've got misfits, we've got gaps in our coverage in order to create our tool chain. If you contrast that with using a Metatool, because we're in control of that, we can make it work smoothly with no gaps, no mismatches, because we're in control of the input and output formats of each step. And not only that, we can do it on our schedule, we can do it exactly to our specifications, and we own the result. So it's quite a difference. Now, there's a lot of talk about legacy modernization because there's a lot of old code out there, and it tends to limit what you can do with the investment that you've made in your application portfolio. So there's a bunch of things you can do. You can totally rewrite, which is risky and expensive. You can migrate, which can be good, or you can take a new approach to this because of the automation that a Metatool can provide. You redesign from scratch, which means that you get the benefits of starting over. You learn from what you did in the past. You start out with a blank slate. But you realize that in your new design, a lot of the functionality from the old system is still usable because we've still got basically the same job to do overall. So what we can do is we can go find chunks of our legacy system that can be salvaged and reused and retrofitted into our new design. And then we fill in the rest of it by writing it from scratch. Now that's possible because, number one, we can automate the assessment process to figure that out and also triage the old system to see what kind of code's in good enough shape that it can be salvaged, for example. And then when it comes time to retrofit that salvaged investment from the old system, we can actually automate that process as well, because that's going to be a systematic set of changes that we need to make. So that's a new possibility for doing legacy modernization that's only possible when you've got this kind of flexible and powerful automation available. You really can't do it with point solutions, for example. Now, we've talked a lot about a Metatool. Let's see what one looks like in terms of its architecture. First of all, we're going to be manipulating computer language content in various different languages. So we need to represent that language content, that code, in a form that we can manipulate. Text isn't going to cut it. That is the text source code that we start with that programmers work with. So we're going to have an internal representation of that language content, which is in fact, if you think about the internal representation as a scheme, it's a meta model of computer languages. And you can create an instance of that meta model in the form of code that you've parsed into the meta tool to create that internal representation. That's actually a model of the original language content. Now, if we're going to analyze it, but we're not going to bring it back out again, then it doesn't much matter whether that internal representation is complete. But if we're going to bring it out because we've applied transformations to it, we've improved its code quality with some rules, or we've translated it, or we've moved it to a different platform, or we've webified it, or whatever we've done, we need to get that code back out again. And that means that we cannot afford to lose anything in that entire process of parsing it to the internal representation and then bringing it back out. So that means that that internal representation has to be complete with no lost information in the process. Now, in order to get to that internal representation, we have to parse the code. So we've got to have language parsers, one per language, which take the text form of the code that the programmers deal with and parses it to create the internal representation version of it. Then we need a rules language, as we've talked about, which manipulates that code content in the internal representation form as its data. A payroll system in COBOL manipulates financial data. Our meta tool is going to manipulate code. In order to facilitate that and to make the manipulation process as effective as possible, that internal representation has to be very rich. It can't just be the raw code. We want to enrich that with lots of pointers and references and pre-digested results and things like that, so that it's really easy once we're writing rules to get out of the code what we want. And then once we've done whatever we're going to do to that internal representation, we've transformed it, somehow we've translated it, whatever, we got to get it back out to text form so that the programmers can pick up on it and start working with it. That means that we need to render it. Now, we use the term render to mean taking an internal representation of code content and creating the text form of it. That's analogous to rendering a JPEG, for example, from its internal form to an actual image, except in this case we're dealing with language content. So we call that rendering. Here's a graphical look at the architecture I just described. On the left side we have the code of the meta tool, and on the right side we have the data that it maintains while it's running. This is typically going to be in memory for speed. If you look at the left side, there's a series of phases that the meta tool is going to execute in order to do its processing. First thing it has to do is it's got to parse everything. So we've got the input phase with a bunch of parsers for all the different languages that we're going to deal with on any particular run. And those parsers get the code into our internal representation, which you see over on the right. And oh, by the way, the rules have to come in to tell our expert system what to do, so they have to be parsed and they have to be stored in internal representation too, because the internal representation we're talking about, it not only can deal with all the languages we're going to manipulate, it is the same for the rules language itself. And yes, that does mean that rules can manipulate rules. Then we've got the processing phase, which does whatever rules tell it to do, because as you can see up at the top there, we've got commands and rules coming in, we've got source language you're going to work with, and then maybe we've got some target language that will tell the expert system more about what we want it to do in terms of the target results that we want. And then there may be a re-engineering phase, depending on what we're doing, to maybe do some code cleanup on the transformed code before it comes out. Finally, we have the output phase with the renderers, one or more, depending on what we're doing, and that has the responsibility of recreating text source code from our internal representation with all of the styling issues that implies. So we've talked a lot about the rules language. Let's see what that looks like. What does it need to look like to do a good job? Well, first of all, we want it interpreted, not compiled. And the reason for that is that we want to play games with early and late binding. Sometimes, for example, if we're processing some code content, we know more after we've done some processing on it about further processing that needs to be done. So we want to delay that further processing until the original processing's been done, and we can figure more out about what we need to do to it. So in that case, we want to post some rules not to be done at the normal processing time, but after that. Similarly, we may want to do some transformations to the internal representation of the code before it goes into the main processing, maybe a little bit of code cleanup, a little code prep that makes it easier for the main process to work. So we would post those rules to be done just before the main processing phase. So you can see that we can play a lot of games with when rules get evaluated, and we want a lot of control over that. And in order to do that, we have to have an interpreted language so that we can decide when that language those rules get evaluated. In terms of the general type of the language, as I already mentioned, it needs to be a general language because we don't know what we're going to do tomorrow. We're lucky if we know what we're going to do today. And therefore, we can't predict what kinds of things this language is going to have to do for us. So we want it very generalized. On the other hand, we want leverage. We want it to do a lot with not a lot of rules. And the way we do that is we enrich it with primitives, which we call meta functions because we're in a meta tool here, we're dealing with meta code, which is the rules language. And those primitives are domain specific. That is, they are specific to the kinds of problems that we want to solve in terms of automating our software development and engineering. So that's great. We got all these meta functions built in, comes with it. But we can't predict what we're going to need in the future for meta functions either. So we want to allow the user to create additional meta functions written in the meta code itself so that the user can extend the rules language's functionality. I mean, imagine if you were writing in C and all you had was the C runtime library. That's not very good. Of course, you create your own functions. Well, we want to be able to enrich our rules language similarly. Now, if you think about computer languages, they are recursively defined. That is, for example, if I'm talking about C, an if statement takes a single statement as its consequence underneath it. But that single statement can, in fact, be a compound statement. So that's a recursive definition of statement. So we need recursive capabilities in our rules language to reflect that because we're going to be dealing with that recursively defined computer language content. So that's another thing we're going to want. And because we're going to be developing rules, we need a debugger for that. So we want a rules debugger built into our meta tool so that we can debug our rules. And we want that to be powerful. We want to have all kinds of breaks, triggers, watch points, etc. What else would we like to have in our rules language? Well, you remember I mentioned that we have to do parsers because we've got to get language content from the text form that the programmers give us into our internal representation so we can manipulate it with the rules language, right? So we want to be able to control that parsing process because we don't want to have to hard code parsers all the time every time somebody needs a new language. So what we want is we want automated parsing, in fact. We want to be able to describe a language in terms of its grammar to the meta tool through the rules language so that the meta tool knows how to parse it. And oh, by the way, languages come in dialects. For example, yes, we've got PL1, but do we have IBM PL1? Do we have VMS PL1? There's many different versions of Pascal out there, for example. There are even some flavors of COBOL. So we need to be able to deal with dialects as well. And then because we are describing to our meta tool how to parse things, we need to be able to trace that parsing process to make sure that the way we did that description of parsing is correct and debug it. Once it's debugged, we're fine. We can pretty much ignore it. Similarly, to get the code back out again, we need our renderers. We want to do the same kind of thing. We want to be able to specify how to render our internal representation back out to text to hand over to the programmers. The same way, we describe what we want the meta tool to generate from our internal representation. That includes things like styling controls, indentation, tabbing, all that kind of thing. We might want to be able to decorate the code on its way out. For example, maybe we want to put in HTML tags to do colorization. So we get our code content out, but it's HTML. We throw it in a browser, and up comes our code with all kinds of nice decoration, colors, bolding, whatever italics, whatever we want, to emphasize whatever we decided in our rules we wanted to visualize. And we might also want to filter it. For example, we might want a version of a great big COBOL program that only shows the control flow, because that allows us to figure out what the overall structure of the program is. And it may be a 10,000 line COBOL module. I've actually seen them. You want to boil that down so that you can actually know what's in there. And when you want to look at it from that point of view, you don't really care about what's called straight line code segments. You're really more concerned with the structure. So we can do a filter in our renderer that says only put out control flow, ignore everything else. And then we get the bare bones just in terms of the control flow. That's one example. Now, we've talked about what we call the text domain of code content, which is the text source files that programmers deal with. And then we've talked about the internal representation, which we think of as symbolic representation domain. And it would be great if we could move between the two dynamically. For example, wouldn't it be great if in a single rule we could take a statement of code content, maybe COBOL, maybe PL1, maybe C, maybe assembler, and render it in the rule to text invoking the renderer just for this statement, manipulate that text somehow using text tools, and then parse it back into internal representation and put it back. That would be a very powerful thing to be able to do, but in order to do that we need dynamic incremental parsing and rendering. And that means that our parsers and renderers need to be able to be invoked that way. And that allows us to do a mixture of both symbolic and text manipulation of language content. More things that we'd like in our rules language. We're going to be manipulating stuff, so we need something to hold it, and that means we need metavariables. And in addition to the usual data types for variables in a programming language, integer, real text, file pointers so we can do file I/O, we want some additional ones that are really specific to us, namely a metatool. We want to be able to declare a variable, metavariable, whose data type is, for example, statement. What that means is that its value at any given time is one or more statements in some language in our internal representation. Similarly, at the expression level. What that allows us to do is it allows us to pass chunks of internal representation around, for example, as an argument to a meta function, which then takes it and does something with it. So you can see that we're really talking about manipulating our internal representation as if it were data, but in an intelligent way that understands and reflects the fact that it's really code. In terms of evaluating rules, well, of course we want if-else. We want iteration so that we can loop through stuff. But remembering that the nature of a code content is recursive by definition, because that's how computer languages tend to work, we also want to be able to do that recursion without really thinking about it much. So we want what we call recursive iterators. We want a statement in the rules language that says, per statement in whatever code tree, do this, apply this rule. That way, we can concentrate on what we want to do to each statement rather than how to get to each statement and apply the rule. Similarly, per expression down at the expression level and so forth. We also want to be able to explore our context. If I'm writing a rule that does transformation, let's say, that transformation may be different depending on the context in which the statement I'm working on actually exists. If the statement is context bound, meaning that it works differently depending on the context it's in, then for my rule to work properly, it has to explore that context, figure out where we are and what situation where this statement is in, and then figure out from that what we want to do to the statement, which could be different in different contexts. That means that we need to be able to navigate from where we are, the statement that we're currently working on, to its context, everything around it, above it, below it, beside it, all the way out to all of the code that we're currently working on in this run, which then requires navigation. And I'll show you an example of that in a minute. Now, what that allows us to do is not only explore context to do context-specific transformations, let's say, or even analysis, it also means that we can go from where we are, knowing what we're looking at, we can go find something in the code that we're working on and fix it. Because since we are where we are and we are looking at what we're looking at, we know that if this other thing exists anywhere in this code, it needs to be fixed. So we can actually go navigate over there and fix it in place. I think of that as tree surgery because we're talking about a tree here. Now, in terms of navigation, we want to be able to navigate either relative to where we currently are, the statement of code content that we're currently working on, or maybe absolute from the beginning of a code tree. Let's say that we want to do a scan of a full code tree while we're working on this particular statement to see if something exists anywhere in this code. Then we just do a scan from the beginning of the code tree. Now let's see what an example of that looks like. Here we are doing some navigation at the statement level, and what you're looking at there in the blue is some C code. Okay, so we start where the little stop sign is, that's our beginning point, and we go, we'll try two here. The rightmost one, we go deeper one statement, then forward one statement, which gets us to the for statement, because the curly brace is a statement. But then more complicated than that is on the left, we go forward one statement. Now, by forward, we mean at the same level. So that means we go from the if to the else. We don't go down into what's under the if because we're going across, not down. Then we go down into what's under the else and forward to get into it. So you can see that we can now navigate, and we could go up too, by the way, and out. So we can now navigate using these capabilities to everywhere in the code that we're currently working on. Now let's take a little bit of a more complicated example. We're going to do navigation at different entity levels. We start at the statement level. That's our first stop sign over on the left there. And we navigate down. We go into the consequence of the if underneath it, go forward a few, go into that statement and start navigating in the expression of that statement. As you can see there, we navigate within the expression deeper, forward, deeper, and that gets us to the I in that expression. And then our navigation capability has a primitive that says, I want to navigate from this symbol to the statement that declares it. So we go all the way out and up and back to whatever statement declared the variable that we're currently looking at. See how that allows us to explore our context in very sophisticated ways if we need to. Okay, more capabilities that we want in our rules language. We want to be able to manipulate text because, first of all, we're going to be dealing with text in terms of analysis results, for example. And as I mentioned before, we may actually want to deal with code content in text form temporarily to do something. That's easier at that level than it is even symbolically. So, and we want to be able to do text comparisons, searches, substrings, all that kind of thing. We want to be able to deal with delimited lists like comma-separated values, for example, because those turn out to be really, really useful in terms of putting out analysis results that can go into, let's say, a spreadsheet for doing pie charts on it or whatever. You may be familiar with regular expressions. If you're a Unix programmer, you know awk and grep and sed and so forth, and all that does, or if you're a Perl programmer, you know Perl regular expressions too. Regular expressions are a way to describe patterns in text and deal with those patterns. So we want that. And then we need to be able to format and scan our text. So for example, we want to put out analysis results in a nice formatted way for human consumption. So we want something like C's printf, scanf, for example. And then we want to be able to organize and store our metadata while we're working on stuff. So we want a database facility built into the rules language which gives us content addressable databases. Now what do I mean by that? I mean that such a database is an in space. If n is 2, we're talking about a vector. If it's 3, we're talking about an array. If it's 4, 2, we're talking about an array. 3, we're talking about a cube. Okay, 4, we're talking beyond our ability to imagine. So in can be anything, depending on what we're doing. And we get to a cell in that in space through a series of subscripts into our cube or whatever it is. Each of the subscripts can be either an integer or, more interestingly, text. And the fact that it can be text means that that's what makes our database content addressable. So for example, I can write up a couple of lines of rules that say, per statement, increment the statement type of the statement we're currently looking at in our database. 2 statements in the rules language, sweeps through the code that we're working on, and gives us tallies of all the statement types that we're seeing in literally two statements in the rules language using this content addressable capability in our database. Then we can pull it back out again. In each of the cells in this database, we want to be able to put data. It could be integers, could be reals, it could be text, or it could be in our internal representation, pieces of that, to store chunks of code content in the database. So that turns out to be highly useful. Another thing is, wouldn't it be great if we could specify a pattern? Let's say we're going to do some pattern matching and replacement on some code content to get rid of ifs, or excuse me, use ifs to get rid of go-tos. We want to be able to specify the pattern. It would be great if we could do that in the actual language that we're working on. So for example, if we're processing C code or COBOL, we specify the pattern in C or COBOL with things in it, which we call wildcards, which are meta, which means that they're unbound, which that's what makes it a pattern. When we apply the pattern match, we bind those, and if the binding is successful, then we've got a pattern match. Okay, that also allows us to provide prototype target code if we're doing translation or if we're doing pattern match and replace with different kinds of code on a systematic basis. More stuff that we want. We want to be able to do I/O, both to the terminal to communicate with our user who's running this meta tool, and file I/O so that we can actually persist stuff across runs and then retrieve it from a rule. That allows us to remember stuff from one module to the next, and in fact it allows us to create a compendium of system information across an entire application portfolio, for example. We want to be able to compare code in its internal representation form and control how detailed or abstract that comparison is. Really drill down or make it very abstract, whichever you like. Because we're doing that comparison on our internal representation, then we really don't care about the original white space, line breaks, comments, that kind of thing. We can tune the comparison to ignore comments, for example. And all of that white space and line break stuff is gone. We're in tree form now in our internal representation, so we don't really care what the original source code text looked like. We can recreate it, but in the meantime, all of those considerations are out of the question. We want pattern matching and replacement facilities. I've already mentioned that. And we want to be able to conditionalize each pattern match based on rule-driven conditions, which means that a pattern can be context sensitive. That means you can build very sophisticated patterns if you need to, or they can be very simple if that's what the job requires. We want to be able to match a sequence of things, like a sequence of statements, for example, which we call a span, or a single entity, and we want to be able to say what are the minimum and maximum number of things in this sequence that this pattern matches. When we get a match, we want to be able to capture a copy of what matched so that we can use that in further matching, or we can reuse that whatever matched in a replacement pattern, for example. And you'll see an example of that in a minute. The fact that we've got all these degrees of freedom in how a pattern match works allows us to go meta, and that allows us to abstract up in terms of how we think about patterns in code. And that means that we're really doing what is sometimes called meta programming, which is a very powerful way to do software engineering. Now let's take a look at an actual pattern match and replacement. You remember I talked about getting rid of go-tos by imposing if and else and do and while. Well, let's take the if-else case. if you look at what we have here, we've got a match pattern, and the blue is C because we're doing this on C, and the red is meta. That's our rules language. And so that's what makes this a pattern. So we're actually embedding meta in C in this particular case. Remember, we talked about it would be desirable to be able to do that. Now you can see why. Then if you look at the replacement pattern, you can see that whatever matched expression in the if is going to be reused in the if in the replacement, and so forth. And that's why this rule will work without mistake. Notice, by the way, that the label disappeared. If this was the only use of that label, we don't need it anymore, so we can get rid of it. Now let's actually apply that to some code. Here we have some actual C code that we're under match on the top there, and notice that it's got a goto under the if. Now the highlighted areas are what matched, and you can see where they matched and what meta entities in the pattern matched what actual code in this particular code instance. And you'll notice that the label gets reused down further in the pattern. So go to label 1, and then you've got label 1 down here with a colon. The way we did our pattern, those have to be the same in order for this pattern to apply. If we do get a match, we can then replace it with our replacement pattern with all of those meta things in the replacement pattern bound to whatever matched in the original code. That's how we do pattern matching and replacement. So let's take a step back up to the 10,000 foot altitude and talk about what all of this means for software development and engineering. In my view, as a practitioner of this, I think that automation is just now beginning to seriously affect the software development and engineering process. And the consequence of that over a period of time is that the number of developers will shrink dramatically. Because of the automation, we won't need nearly as many developers as we do now. At the same time, because we're automating the easy parts and the boring parts, what's left is tough. And that means that the level of the remaining developers is going to be much higher in terms of talent and experience. They will either be working on the automation tools, or they will be working on systems using those automation tools to create and maintain the systems, application systems, for example. Because of the level that they work at and their level of talent and experience, they will be in short supply, which means that they will work from wherever they are, and they will be, their compensation will be global in scale, which means that offshoring is basically going to go away, because offshoring is made possible by cheap labor. When the labor's gone and you're reduced to very high level, very skilled labor, that's no longer viable and offshoring disappears. So let's summarize. We're talking about applying to the software development and engineering process a rule-driven expert system approach to automation. It should be able to manipulate both computer languages, data, and text. And the objective is to capture expertise in terms of code analysis, re-engineering, and translation in the form of rules so that we can then deploy that expertise using our expert system and those rules. We want leverage because we want to be able to create a software engineering tool quickly and automate whatever it is we need to do on any computer language we have to deal with. Leverage is the key. They have to be easy enough to create rules so that you can do throwaway rules, although typically, even when you think you're going to throw away some rules, you probably want to keep them because another problem may come along day after tomorrow that's very similar, and you can reuse those rules. But also, at the same time, the rules have to execute fast enough that we can inject this thing into our production cycle for, let's say, for example, injecting software quality analysis on every developer's desk all the time, 24/7. That means that the rules have to really go fast, because otherwise we're going to slow people down. We need to be able to use the rules language to manipulate any language, including pattern matching and replacement and what we call tree surgery, which is reaching out into the tree of internal representation and changing things. We want to automate the parsing and rendering processes so that we can add new language and language combinations quickly and fine-tune the ones we already have. The bottom line of all of this is that what you can do with a meta tool like this is only really limited by your imagination. It's a very rich environment in which you can use rules to automate what you're doing. And if you have a rich enough rules language and set of tools built into the meta tool, then you can do pretty much everything you can think about that's even vaguely automatable.
Thank you very much, Steve. Zintro members, feel free to contact Steve directly. You can see his Zintro profile link on your screen. On behalf of Zintro and our over 180,000 members, Steve, thank you very much for sharing your insights. This closes today's presentation. I wish you all a very nice day.